Let's look at some of the other events here. Let's kind of zoom in a little bit closer. So we're still speaking about the phases of the cardiac cycle, but we're going to focus a little bit different and look at the pressures. So during phase one, and just to remind ourselves, this is ventricular filling. This is the middle of diastole. Let's look at what happens to the pressure in the atria and the ventricle. So during phase one, we've got the atrial pressure rising slowly as the blood spills out of that chamber. The ventricular pressure is still quite low, and we have a small rise in the ventricular pressure at the end due to the rise in the atrial pressure. So basically, these two graphs look the exact same because as the atria squeezes, remember we said towards the end of diastole, the atria begin to squeeze to get that last bit of blood out, then that creates a rise in the ventricular pressure as well. So towards the end of phase one, we see this kind of bump in the pressures, and that is indicating the squeezing of the atria towards the end of this phase, and that creates a rise in ventricular contraction as well towards the end of this, not contraction, but the rise in the pressure due to that squeezing of the atria, squeezing blood down into the ventricle. During phase two, we have a rapid rise in ventricular pressure. Both valves are closed here, but the ventricle is contracting. The atrial pressure will fall because the atria are no longer contracting, nor are they spilling blood down into the ventricle, so they're not squeezing, so the pressure drops. But as the ventricles contract, the pressure in the ventricle rapidly increases. And again, that is what is required to create the pressure gradient that will create the flow of blood, which happens in phase three. So that pressure is gradually rising, or rapidly rising rather, in order to create that pressure gradient. So during phase three, we now have ventricular pressure falling as the blood leaves the ventricle and moves out into the artery. And then the atrial pressure will further fall until the end of systole. Remember, phase two and phase three are comprising systole, and towards the end of systole, that's when we finally have the atrial pressure rising again. But for the most part, it will fall further as the ventricular pressure rises to get that blood out, but then eventually falls. So we can see this kind of sharp peak in the ventricular pressure, and that is indicating that blood is moving from the ventricle into the artery. Let's talk about what's happening in the aorta. So the aorta is a unique situation. The aorta is where blood moves in order to go out to all of our peripheral vessels and tissues. And so the pressure that's going into the aorta is very important as it relates to cardiac output and to the function of the heart. So during diastole, the aortic valve is closed. Remember, the semilunar valves are closed as the ventricles fill. Blood is leaving the aorta, and then pressure begins to fall. Okay, so we're looking here at phase four and phase one as we talk about diastole. We can see the line here, the blue curve is representing the aortic pressure. So as the semilunar valves are closed, the pressure in the aorta drops off, and that drop off is coming all the way from phase one. So phase one, the aortic valves close here, the pressure drops off all the way till it gets back over to phase two. This is the lowest point in the cardiac cycle in terms of the pressure in the aorta, and this is what we describe as being the diastolic pressure. So when we measure your heart, your blood pressure, we're actually looking at these aortic pressures. So the diastolic pressure is the lowest recorded pressure in the aorta, and that is at the end of diastole. So that's this pressure here, and that is the bottom number in your blood pressure reading. The systolic pressure is a little bit different. So this is when the aortic valves open. So remember, systole is going to be phase two and phase three. We've got the aortic valves opening as the ventricles empty. Remember, phase three is ventricular ejection. So as the ventricles eject blood, the semilunar valves open, Pressure is going to rise rapidly as the ventricle squeezes, but then it's going to drop off as blood leaves the chamber. And then we have the closure of the aortic valves once again. And so there's a slight bit of backflow that hits the end of that aortic valve as it closes, and that creates this dip in pressure that we call the dichotic notch. So the dichotic notch is a slight dip in the pressure of the aorta as the blood hits against the back of that closing semilunar valve, that closing aortic valve. Now, at the top of this pressure curve, we can see that this is where we record systolic pressure. So this is the highest recorded pressure in your aorta, and that's going to be the top number in your blood pressure reading. So your blood pressure reading is really looking at the highest pressure, which is systolic pressure, over your lowest pressure, which is your diastolic pressure. And so it's really looking at what's happening in the aorta as blood moves through these cardiac events, these cardiac cycles. And although we're not looking at the aorta specifically to read these pressures, we're looking in one of your peripheral arteries, so the brachial artery in the upper extremity. This is giving us a representation of what these pressures look like in terms of what's happening in the aorta. So we can describe mean arterial pressure as being the average aortic pressure occurring during the cardiac cycle. This is really an average between systolic and diastolic. We'll talk about how we calculate mean arterial pressure, although that's not as important, but it's really a good understanding of the driving force that's moving blood throughout the vascular system. So if you've got a very low diastolic pressure and a very low systolic pressure, that means you don't have a very good driving force that's moving blood through your systemic circuit. Likewise, if you've got a very high systolic pressure and a very high diastolic pressure, that is indicating there's narrowing in your arteries. So the blood is under extremely high pressure. Again, that is not an ideal circumstance, but it's going to tell a story to clinicians, and that's why we measure your blood pressure. It's giving us a picture of what kind of driving force is pushing blood throughout your systemic circuit. And in the case of high blood pressure, it's actually telling us what the vessels look like throughout your systemic circuit. The aorta is going to be a large elastic artery, and we'll speak about how the aorta is a pressure reservoir. It's going to be able to store some pressure, so it expands as blood leaves the ventricle and moves out into this artery. And then it's going to relax during diastole when the walls of the ventricle are relaxing, when the semilunar valve is closed, when blood is no longer moving into the aorta, it's going to recoil, and that recoil is what's going to create the force that keeps blood moving continuously throughout the entire cardiac cycle. So another way to explain that is, it would be, we would kind of want to think that when the semilunar valves close, that we no longer have blood being forced throughout the systemic circuit. That is not true. When the semilunar valves close, the elastic nature of this aorta kind of recoils on itself, and that creates this propelling force that keeps blood pushing throughout the systemic circuit, even when that semilunar valve is closed. Okay, and this illustration kind of summarizes that even further. So during systole, remember the heart is ejecting blood into the artery. So we've got continuous flow coming from the left ventricle, moving into the aorta and moving out to our systemic organs. And as the aorta expands to accommodate that flow, it's going to kind of expand and store some of that energy in the elastic walls. During diastole, when the semilunar valves close, so we can see the aortic valve has closed here, there's no longer that flow coming from the left ventricle, and so we would kind of want to think that perhaps the flow would decrease as this valve closes, but that is not true. The energy that's been stored in the elastic walls of the aorta is now going to recoil on itself, kind of like a spring or an elastic band, recoil on itself, and that creates the flow or the propulsion to keep blood moving to our systemic organs uninterrupted in a continuous fashion, even though the semilunar valves has closed during diastole. So this is why the aorta is so elastic in its nature. This is allowing it to capture some of that energy. It's acting as a pressure reservoir here so that it can then unleash that energy as it recoils, and that can keep flow uninterrupted out to our systemic organs. And that is why the aorta is so elastic in its nature, in order to keep blood flowing throughout all phases of the cardiac cycle.